Welcome to the deep dive. For years, talk about AI versus human intelligence, well, it often felt a bit abstract, didn't it?
Definitely. Lots of talk about potential, maybe some philosophical arguments.
Right, almost like hand-waving.
Yeah.
But our sources this week, they're showing a fundamental shift. It looks like we've moved from, vibes to actual measurements.
Yeah, hard data.
Exactly. We're digging into a big multi-year study that used a really demanding benchmark. The International Olympiad on Astronomy and Astrophysics exams, the IOAA.
And this isn't some lightweight test. It's a world championship for really smart high school students doing high-level science.
Okay, so what's the big headline from this study?
Get this. The latest AI models, we're talking GPT-5 and Gemini 2.5 Pro, they repeatedly hit gold medal level performance.
Gold medal against the world's best student competitors.
Yes, across 4 years of testing, in some cases actually ranking first on certain metrics. This study gives us the first kind of repeatable, reliable scoreboard for this level of scientific reasoning. It sets a completely new baseline.
A new baseline. Okay, that's the key phrase. So, our mission for you today isn't just to, marvel at the gold medal. We need to unpack how these models did it.
Right. Where did they really excel?
Yeah, in the tough stuff, the derivations, the data analysis, but also, and this is crucial, where's the weak spot? Where's that brittle Achilles heel?
That's definitely there.
And we'll pull all that together into a practical playbook, how you can actually work with these incredibly powerful, but well, still flawed systems right now.
Okay, so first, to really get why this is such a big deal, you have to understand the IOA itself. It's tough.
It's not just memorizing facts.
Not at all. It's all about deep reasoning.
Yeah.
The problems are long, they're conceptual. You need physics, math, spatial thinking all combined. Simple recall gets you nowhere.
So what are the actual parts of the competition?
Well, there are 3 main bits. First, the theory paper. That's where you see step-by-step derivations, complex concepts. Second, the data analysis exam. This uses real plots, noisy data. You have to analyze it, measure things, and then argue for a physical meaning.
Makes sense. And the third part?
That's the observational section. It's hands-on, using telescopes, and naturally, the AI didn't do that part.
Right. Can't quite get GPT behind an eyepiece yet, so we're focusing on the theory and data analysis parts then.
Exactly, because those really capture the core of what astronomers do day to day. Celestial mechanics, cosmology, interpreting light curves, that kind of thing.
Which means the AIs weren't just guessing. They were showing complex, multi-step reasoning.
Precisely.
Okay, so let's get to the scores. The results from 2022 right through to 2025. You said they matched or beat the top students consistently.
Consistently. And we need to be clear about what gold medal means here. The bar is set really high.
Oh, high.
It's defined relative to the humans. You need a score that's 160% of the human median score for that year.
Wait, 160% of the median.
Yep. So significantly better than the average top performer. And the sources confirm GPT-5, Gemini 2.5 Pro, and another one, OpenAI o3, all hit that level on the theory parts.
Wow. 60% better.
Oh,
Is that just beating the curve? That's like redrawing the curve entirely.
pretty much.
What's really interesting to me, though, is you said it wasn't a clean sweep for one model. The results showed differences.
Exactly right. It was more of a split decision between the top contenders. It shows their underlying design choices actually matter.
Okay, how so?
Well, GPT-5 really stood out in data analysis. It averaged about 88.5% on those tasks.
88.5. What was it doing well there?
Things like reading plots accurately, generating plots from data, cross-checking numbers against the visuals. The researchers think its strong multimodal capabilities handling images and text together gave it an edge there.
Okay, so GPT-5 for data visuals. What about Gemini 2.5 Pro?
Gemini often did better, or at least edged ahead in the theory sections, especially when the exams leaned heavily on geometry and spatial intuition.
Ah, interesting.
Well, the sources point to the 2024 exam. It had a lot of spherical, trigonometry, tricky stuff, and plotting ground tracks. Gemini actually topped the theory scores that year.
Spherical trigonometry. We'll come back to that, I suspect.
Oh, definitely.
So the takeaway isn't just AI is good. It's that different AIs are good at different kinds of scientific reasoning.
Precisely. It means research teams need to think about these models like specialized tools, not just one big AI monolith.
Right. If you're doing survey analysis, maybe checking lots of plots, GPT-5's accuracy there is a big plus.
But if your work involves, say, complex orbit calculations, satellite positioning, maybe Gemini's edge in geometry, at least for now, is more valuable.
Okay, let's shift gears a bit. How are these things actually solving the problems? It's not just spitting out an answer, is it?
No, not at all. That's
Yeah.
the impressive part. They're doing multi-step derivations. They take a word problem, translate it into physics equations, figure out the right coordinate system, like should we use equatorial coordinates or the local horizon, and then manage all the units consistently through pages of work.
Can you give an example, like one of a hard theory problems?
Sure. One example required calculating the path of the greatest eclipse and the contact times for someone at a specific latitude on a specific date.
Okay, that sounds hard even for a human.
It is. It involves using the spherical law of cosines, doing vector projections onto the celestial sphere, and handling really tricky time conversions. Switching between local sidereal time and universal time, UT. That's way beyond simple math problems.
That spherical law of cosines, I remember that from astrophysics class. Brutal. Doing it by hand, you just hope for partial credit. Are the AIs generating work that you can actually follow? Like, could a scientist use it?
That's exactly what impressed the scientists who graded these things. The outputs are readable, the steps are logical.
Really?
Yeah, they keep units consistent, they make reasonable approximations and state them. And crucially, they show enough work that even if they make a small slip, they'd still get partial credit.
Wow.
It's that kind of bread and butter, rigorous reasoning you need from a good research assistant.
And what about the data side? You mentioned exoplanets.
Right. A typical data task might be, here's some noisy data from a telescope looking at a star, a light curve. Find the signal of a planet passing in front.
So find the period, clean up the data, fit a model of the transit.
Exactly. And then argue if the result actually makes physical sense. And this is where GPT-5's better performance in just reading and making plots accurately with fewer errors becomes a real practical advantage, especially if you're automating searches through huge data sets.
Okay, wait. You're painting a picture of incredible competence. Gold medals, readable derivations, good data analysis. So why isn't this the end of the story?
Right. If they're that good, why aren't we just, handing over the keys to the astrophysics department?
Yeah, where's the catch? You mentioned an Achilles heel earlier.
Yes. The same study that delivered the gold medals also carefully documented where these models fail. And the failures aren't random. They're systematic. They kind of rhyme.
Rhyme, how so?
The biggest, clearest weakness is in geometric and spatial reasoning. And that often gets tangled up with problems in keeping track of time accurately. The key technical term here, spherical trigonometry.
Spherical trigonometry again. Okay, help me understand this. These models handle incredibly complex abstract algebra, things that seem much harder intuitively. Why does geometry on a sphere trip them up?
That's a great question. It seems to boil down to maintaining consistency across different coordinate frames. Think about it. Astronomy happens on the celestial sphere.
Right, this imaginary sphere around the Earth where we map stars and planets.
And it's constantly rotating, shifting relative to us on Earth. The models often mess up when they have to translate angles and positions between different frames, say, from the celestial equator to the observer's local horizon.
So they might, get the angle wrong, put something in the wrong place on the sky.
Exactly. They might pick the wrong angle in a spherical triangle, miscalculate where an event like an eclipse happens, or maybe forget to account for tiny shifts like precession over long timescales.
So it's not the pure math calculation itself, but applying it correctly in that 3D dynamic space.
Yeah.
That feels counterintuitive even for people sometimes.
That's a good way to put it. The weaknesses fall into these buckets. 1, geometric errors, bad vectors, wrong angles, putting things in the wrong spot.
Yeah.
2, persistent timekeeping issues, mixing up different kinds of years like tropical versus sidereal, or just small unit slips that add up over time and mess up predictions.
Okay.
And the third one is interesting. Sometimes the model uses a formula that looks mathematically correct, elegant even, but it just doesn't apply to the physical situation. The researchers called it pretty math, wrong world.
Pretty math, wrong world. I like that. It highlights the need for physical intuition.
Exactly. Astronomy is just so geometry heavy. You're on a sphere, looking at a sphere, tracking movements across spheres.
So the practical takeaway from the study, based on this hard data, is keep a human in the loop, especially for the geometry, the timekeeping, and just the overall sanity check.
Yes. That human intuition for whether something makes physical sense is still the crucial backstop.
Okay, so what does this actually mean for scientists going forward? It's not about replacing humans, clearly.
No, definitely not handing over the lab, but it absolutely means accelerating the lab. Thinking of the AI as a
The
co-scientist.
co-scientist. I like that framing. So how do we define the roles?
We can actually map out a practical division of labor right now based on these findings. Use the AI where it demonstrably excels complex algebra, checking long derivations, processing lots of data, especially visual data.
Okay.
But you have to watch it like a hawk, where it's known to be brittle specifically, spatial geometry, spherical trig, and precise time logic.
So concrete roles,
Mhm.
what can it do reliably?
It's an amazing derivation assistant. Got a really long, tedious algebraic manipulation to get some constant, offload it. The AI can check dimensions, suggest different ways to write the result, catch simple mistakes humans make when they're tired.
That alone sounds useful.
It is. It's also a great parameter explorer. Tell it to check a wide range of values for some physical parameter in your model. It might surface weird edge cases or inconsistencies, like catching that drifted unit in a long calculation that you might have missed.
And you mentioned the data analysis, the plotting, the plot auditor role.
Yes, especially thinking about GPT-5's strengths there.
But hang on, if it's good at plots, why does it need a human auditor? Shouldn't it catch its own mistakes with axes and legends if it's truly multimodal?
Logically, yes, it should. But the study shows it still makes mistakes systematically, maybe fewer than older models, but still.
Still making them.
Right. So the plot auditor role is like a necessary, maybe temporary quality control step. Let the AI generate the first draft of plots, it's fast. But a human absolutely must check that the axes make sense, the units are right, the legend is correct before that plot goes into a paper or a presentation.
Because a small plotting error in science can be catastrophic.
Exactly. That error rate isn't zero yet.
So this all points to a key safety mechanism teams need, right?
Absolutely. We need what you could call a geometry gate.
A geometry gate. Explain that.
It's simple, really. For any problem that involves spherical geometry, transforming between coordinate systems, or really precise timekeeping, the workflow should be AI proposes, human verifies.
The human checks the geometric setup, the time conversions.
Yes, you build in checks, like automatically flag any solution that, say, treats a tropical year and a sidereal year as the same thing, because they aren't. That defines the productive, safe boundary for using these tools in 2025.
Okay, this is really practical. For listeners who want to actually, kick the tires on this themselves and see that boundary.
You can give them a specific problem to try. It's designed to test exactly these weak points, the geometry and timekeeping.
Perfect. Little diagnostic test.
Okay, here's the basic prompt outline. Really emphasize the geometry part when you give it to your model. An observer is at latitude 30 degrees north. They're watching a solar eclipse. The sun's declination is minus 10 degrees. The moon's shadow hits the Earth, and the point right under the shadow center, the subsolar point, is at latitude minus 7 degrees.
Okay, got the setup. What's the task?
Compute the local circumstances for the maximum phase of the eclipse for that observer. Estimate the time of greatest coverage. You must use spherical trigonometry on the celestial sphere, state all your approximations clearly, and report the contact times in universal time, UT.
Okay, that definitely pushes the geometry and time buttons. So when someone runs this, what should they look for?
Two main things. First, did the model set up the spherical triangle correctly? You need one connecting the observer's zenith, the celestial pole, and the sun's position to solve this. Did it apply the spherical law of cosines the right way?
Right, the geometric foundation.
Second, and critically, time. Did it correctly distinguish between sidereal time related to star positions and solar time related to the sun when it calculated the times and converted them to UT?
And if it messes up that time conversion or fumbles the spherical triangle?
Then you've just found it. You found the current practical boundary of AI versus human intelligence in complex scientific reasoning right here in 2025.
That's a fantastic concrete test.
So wrapping this up, the core takeaway from the IOAA study is huge. It's the first really broad, credible benchmark in a scientific field where you can't just hand-wave, you have to show your work.
And that gold medal performance isn't the end goal.
No, it's the new baseline. This is the level of competence we now expect for complex scientific derivations from AI.
But the good news, you could say, is that the failures, the geometry, the time logic seem like technical problems, not some deep, unknowable conceptual gap.
Exactly. The study suggests these are teachable issues. You can improve them with better training data, maybe integrating visual tools like a virtual scratchpad for geometry into the AI's process.
So we're moving from these big philosophical debates about AI consciousness to a much more practical, technical punch list of problems to solve,
That's right. Fix the spherical trig. Nail down the timekeeping.
which leads to a final, kind of provocative thought. The study nails down the current limits: spatial consistency, precise time logic. What happens if, or maybe when, the next generation of AI models does fix this, if they integrate those visual tools and finally conquer spherical trigonometry? What does it mean for the human scientist when that last major systematic failure mode in complex scientific reasoning just vanishes?
That is the question, isn't it? What's the role then? That's definitely something to chew on as you start working with your own AI co-scientist this week.